So now I'd like to introduce Professor Kaća Bradonjić, who's from Wellesley College. And you may have noticed that we have some titans in the field of history and philosophy of general relativity here. But we also have some really brilliant young minds who are great scholars and or relativity theorists. And everyone has a particular connection to the theme of this conference. Kaća was a student of John Stachel, a relativity theorist who was also deeply involved in the history and philosophy of general relativity. So even the brilliant new faces in this field are people who have a connection to this tradition that also includes people like John Norton and Michael Friedman. So without any further ado.
So my talk today is about unimodular invariance, and before I start, I gotta say that I'm really impressed with London because I have a feeling that this Rotman Institute, all this thinking is kind of spreading around. 2 days ago, I was on a bus. I was taking the city bus number 2, and this woman was trying to walk along the bus while it was decelerating. And she didn't seem like a relativist to me, but and she was sort of scrambling to get across. She says, "Oh my God, it's like gravity is pulling me back." I thought, if you only knew. So I'm going to begin, so I'll give you an outline. First, I haven't given this talk to philosophers, and I'm assuming most of you are philosophers and historians of physics. So I'm going to take it easy and introduce some basic structures we use in general relativity. Then I'm going to discuss what unimodular invariance means, and then I'm going to try to convince you that adopting unimodular formalism is actually very advantageous. So we'll start simple. We know that in relativistic physics, physical events are represented by points of a four-dimensional differentiable manifold. That's sort of a cartoon picture of it. At each point, we can attach a tangent vector space, and in that vector space we can pick a basis. And just introducing the basis doesn't imply any orthogonality in the basis or length, because we haven't introduced the metric yet. There's also a corresponding cotangent space, where we can pick a basis of covectors, which are dual to the regular vectors. So they nicely can be, the particle two can be delta function. And also in the tangent space, the basis, which is an ordered basis actually, defines a little volume. So in sort of 2 dimensions, it's going to be parallelogram. In 3, it's a cube, and in 4 dimensions, it's something called parallelotope. If you can't hear me, tell me to speak up, okay? In the back, can you hear me in the back? Speak up a little? Okay, I'll try. Now, all the other fields defined on M can be expressed in terms of their components with that chosen basis. Now, we know that in general relativity, there is nothing that individuates the points of the manifold from one another. So if you transform the underlying points, if you do an actual transformation of the points, whatever laws or physical theories you have on M should be unchanged. Now, the diffeomorphisms of these transformations of points on M, they also induce transformations of the physical components of all the geometric objects with respect to some order set of basis vectors which you chose. And they induce these transformations of the elements of the general linear group. Now, I want to make a point and distinguish between the active point transformations and the coordinate transformations. One can express the active transformation of a point in terms of a coordinate transformation, which is what has historically been done, and then interpret those changes in coordinates as changes in the frame of reference. So that was Einstein's sort of train of thought. But I want to emphasize that point transformations are more fundamental. In a coordinate language, which I'm going to keep using because it's easier, general relativistic theories are invariant under all invertible differential transformations of coordinates, and in general they're represented, the transformation matrix are represented by lambda, and the only condition is that the determinant of the transformation matrix is not 0.
A little louder?
Louder?
Keep it up.
Okay, I'll try to sustain it. Now, we classify different geometrical objects based on their transformations under this And so what we have usually scalars which don't change. We have tensors, we have connections, but we also have these things called scalar densities and tensor densities, which have a factor that's a power of the Jacobian transformation. So these are called scalar densities and tensor densities. Okay, so that's our little toolbox of things that we have. Now, general relativity, in its second order formalism, is based entirely on the metric tensor. And since I'm going to be introducing a lot of different fields, I figured I'd put a face on them. So I'm going to be using the card analogy. So the metric is the king of hearts. And all the field equations, everything is expressed in terms of this metric tensor. And I wrote the field equations denoting the Ricci tensors and scalars with K, because Schouten distinguishes between metric-based curvature and the connection-based curvature, so I'm sticking with that convention. This is the usual textbook instruction. However, we do have first-order formalism, which distinguishes between two a priori independent fields, the metric tensor and the affine connection. So I'm going to briefly go over what they actually represent. So the metric tensor represents the chronogeometry of space-time. It tells us how measuring clocks and rods behave. It distinguishes between time-like, space-like, and null vectors at a point, but not at different points, so it's a local quantity. It also creates a one-to-one correspondence between the basis vectors and covectors. So we can transform, we can move from one space to the other. Affine connection, on the other hand, represents the inertial gravitational field and describes the paths, or actually the curves, which are parameterized paths of freely falling particles. By freely falling, we just mean under the influence of gravity only. It also defines the affine covariant derivative, which is used to generate autoparallel curves. It also allows us to parallel transport vectors in arbitrary directions, and such transport is in general path dependent, and the path dependence is manifest in the curvature tensor, which I denote the R this time to distinguish it from the metric-based one, and this one depends only on the affine connection. So you know that if you transport a vector in a loop, you're gonna come back and you might not get the same vector you started with. It also determines the equation of the geodesic deviation of neighboring autoparallel curves, which is responsible for describing the tidal forces. And I have geodesic in quotation because the geodesic is the shortest possible path, or the curve, which is a metric concept, whereas the affine connection defines the straightest path. But because this is so commonly used, I left it there. And then again, we start with these two as a priori fields, and then we can impose a condition of metric affine compatibility, and if the covariant derivative of the metric with respect to affine connection vanishes, then our affine connection has components which are Christoffel symbols. So this is just a generic, sort of a general metric affine compatibility. Okay. Now, as John Norton can attest, and he can talk to you about it, the road to general covariance was bumpy, and Einstein sort of backtracked a lot of times trying to figure out what should be the underlying symmetry group. And I think this code, since I started reading literature on history of physics, I keep coming across this over and over and over again. And the key part of this code is that he says that the sum of all coordinate substitutions in any case includes those which correspond to all relative motions of three-dimensional systems of coordinates. So he's concerned with frames and observers, and they're represented in his language with coordinates. So all he cares about is that the coordinate transformation include the relative, all the possible observers that he's concerned with. Now, the alternatives to diffeomorphism invariance, and one of them is unimodular invariance, and I'm partial to it because my PhD thesis for John Satchel was in unimodular invariance. And it's basically adoption of the volume-preserving subgroup of the diffeomorphism group as the underlying symmetry group. And if you want sort of an intuitive understanding what that means, if you think of a volume as sort of in this four-dimensional space-time, a set of points which represent events, and you have volume-preserving transformations, in a sense, you can think of it as permutations of the points. So the number of points remains the same, you just transform them one at a time. Now, the unimodular diffeomorphism of the base manifold induced transformations again in the components of geometric objects represented in terms of their components with respect to the bases we chose, but these are the elements of the special linear group.
Could you
And
just
then-
back up one slide
Yes.
before that vanishes? Thanks.
Oh, sorry. I can send you the PDF if you want.
I just want to understand it now.
Okay.
Just one more second, fine.
Okay. I have a lot of slides and lots of pictures. I'm afraid I'm not going to get through them. So if I'm going too quickly, please tell me. Now, if you have a unimodular theory, this is what I'm calling unimodular theories, those will be invariant under the group of these volume-preserving transformations. And symbolically, what that means is that now you include all the transformations which have a determinant of 1. So the Jacobian has a determinant of 1. Now, I got my PhD in 2012, and I was quite taken by the beauty of what I saw as the beauty of the formalism we're going to talk about today. And I always wondered, why didn't Einstein think of this? Because it's so pretty. It's so, it was about simplicity and so on. And so, a couple of years after this, so this is 6 months ago, I started digging around to see. And coincidentally, that's the time that Einstein's papers went online, so I then searched them. And I came across John Norton's paper on the development of general covariance, and somewhere in a footnote somewhere he mentioned that Einstein wrote this paper in November, in November of 1915, where he actually considered there was this restricted symmetry group. So I was very happy, I felt gratified, I felt sort of, what I was working for was something worth looking at. And so there really is a really nice paper, and I'm just gonna, I guess you can read it yourself. But he says, okay, what happens if I restrict my coordinate transformations to those which have unit determinant? And then he goes on to say that nobody who really grasped it can escape from its charm because it signifies the real triumph of the general differential calculus as founded by Gauss, Riemann, Christoffel, Ricci, and Levi-Civita, which is the quote that Norton stole my thunder with. You can imagine a graduate student after 5 or 6 years really working on something and not knowing whether this is worth anything, reading this code. You can't imagine the grin on my face. It's highlighted in pink in my copy. So why is it called volume preserving symmetry? Well, in general relativity, if you have this basis and it creates this little parallelotope, the volume of the parallelotope is not invariant under a general linear group. And so what you end up having to do to get an invariant volume, you need to multiply it by the square root of the determinant of the matrix, square root of the negative determinant of the matrix. So in his sort of a review paper of relativity, this is one of the points that Einstein clearly makes. I'm pretending to be a historian of physics. I was inspired by Norton, so some of these slides were modified last slides. Now, if you adopt unimodular invariance, this infinitesimal volume is preserved under the special linear group. And so even though the basis vectors may transform, the volume stays the same. And Einstein notices this in his November 4th paper. He's quite happy about it. The nicest thing, well, maybe not the nicest thing, but a really beneficial thing is that once you adopt the unimodular group, the transformation is the physical fields now can be classified in such a way that densities just go away. Because the density is transformed with this factor of the Jacobian up front to the power of W, which is the weight of the density, called the weight of the density. Those guys just go away. So you basically are left with scalars and tensors. Connections are still there, they don't change. So that greatly simplifies or reduces the number of different things you can deal with here. Another thing that was very important to Einstein is that these transformations included rotations. So it says here that the new theory complies with the relativity of motion follows from the fact that among the permissible transformations are those that correspond to a rotation of the new relative to the old system with arbitrarily variable angular velocity, and also those where the origin of the new system performs an arbitrary prescribed motion relative to that of the old one. So he was concerned with having rotations included, and so was, I guess, happy that the unimodular ones were including those as well. Now I'm going to talk about benefits of the unimodular invariance by mixing this. I'm going to tell you what Einstein noted in his paper, and I'm going to show you how he could have built on that in terms of what I did for my PhD. So my PhD work was inspired by John Stachel, and it was really influenced by work of Weil, as well as the axiomatic construction of the pseudo-Riemannian spacetime from hats of massless and massive particles. It was done by Ehlers, Polarity, and Schill. So what we did is we developed a framework for relativistic theories in terms of conformal and projective structures based on this unimodular formulas. And we call it unimodular, conformal, and projective relativity. I'm going to refer to it as UCPR. So we'll do metric structure first and then the affine structure afterwards. So we know even in general relativity, we can take the metric and we can decompose it, or we can express it as a scalar density, which corresponds to the square root of the metric, the minus sign, and also the conformal metric. But this breakup is not unique. What Einstein figured out in the November 4th paper is that because the volume element is invariant, the old invariant volume, which included a factor of square root of minus g, is also invariant, so the conclusion is that the determinant of the metric is also invariant. Now, I'm going to sidetrack just a little bit, because how many of you have heard unimodular theory before? Lee's the only one, too. There are three. There are lots of theories that go under the name of the unimodular theory. So I'm going to just tell you, I split them into three classes. I'm going to tell you what they mean, and I'm going to tell you which I think is the one. So the first one is the one where the metric has a determinant of -1. So I listed, there's a lot of literature on this. There's sort of a revival of unimodular theories right now, so I couldn't include the long bibliography. But the early ones, for this particular assumption, the earliest ones I could trace was 1989 by Unruh and Walden. I don't know if I'm pronouncing that.
Yeah, Raphael Sorkin is before everybody.
Is
He
it?
forgot to publish.
Oh, is he? Well, was he before Einstein and Finkelstein?
No, but
1971?
he was before anyone else.
Okay.
He just didn't talk about it.
Well, actually, some people would quote Einstein as being the first one to do this,
Sure,
because in
yeah,
his major review paper, he expresses all the field equations in a coordinate system in which the metric determinant is -1.
Sure.
But then he says, well, it doesn't mean that I don't have general covariance because I can always switch to another.
No, but he had the nine-field equations
Yeah, it's something.
version. So fairly Einstein is the first, so I think that's it.
Yeah,
But then Finkelstein and then Sorkin.
came up, right. So the other version is that G is a constant, so it's not specified in terms of its value, but it's a constant everywhere. So you have Einstein and Finkelstein, and then lots of other ones. And one interesting thing that I noticed that Einstein and Finkelstein don't get quoted much, especially not by field theorists. You know, the particle physicists who are using this, people who do quantum gravity. That paper is somehow forgotten. The relativists will quote it, but nobody else does. I don't think Wall does. I don't think these guys do. Do you? Did you cite it in your unimodular theory paper?
I don't think I did.
No, shame on you, Lee. Shame on you.
I'm a huge fan of the Finkelstein.
The last one is this version in which G is an invariant. So Einstein is the first one. This was developed before general relativity was in its full-blown form. And it's the one that I'm going to be talking about. And the reason I'm choosing this one is that even though it's true that if you have a theory with a constant metric, that theory will be invariant under unimodular invariance, under the unimodular transformation, sorry. But the reverse is not true. If you have, if you're dealing with, if you adopt a modular group as the symmetry group, the only thing you're getting is that you get an invariant metric. But it doesn't fix the metric. It doesn't make it constant. It doesn't impose any of the other conditions. So the first two are very restrictive. The last one is the least restrictive, and it's the one that Einstein considered, and that's the one that I'm going to talk more about. Okay. Now, I already told you that we can split the metric into this sort of conformal metric and the conformal factor up front, which is related to the determinant. in general relativity, those two things are densities. In unimodular formalism, and specifically in UCPR, the scalar factor up front is a scalar. It transforms as a scalar, and the conformal metric is a tensor. And you can treat them as independent fundamental fields, and you can construct the metric from those two. Now, the scalar field, so I'm somewhat redundant here, but I figured if I repeat enough times, you'll remember better. Works on my students. It's a scalar field, possibly dynamical, and it provides a measure of a 4 volume of that parallelotope created by the basis vectors. And again, it plays the same role in UCPR as a determinant of a metric does in GR. And just to make sure you don't forget that under general linear group, it's a density, and under a modular group, the special linear group, it's a scalar. So all the observers will agree on its value at that point. Now the conformal metric tensor, it's a conformal invariant second rank tensor with we can just leave it determinant. Again, in GR, it's under general linear group, it's a density, and the special linear group, it's a tensor. When you construct the metric for them, those under the transformations of the coordinates, those factors cancel out. So metric ends up being a tensor. But in UCPR, it's a tensor to begin with. And so some physical, what does it actually physically represent? Well, it determines the null hypersurfaces corresponding to wavefront characteristics, or the null hypersurfaces of constant phase for zero rest mass fields. John Stachel forbids me to talk about zero rest mass particles. He thinks that waves are more fundamental for the massless cases. But essentially it determines the causal structure of space-time. It allows us to distinguish between space-like, time-like, and null vectors at a point. It allows us to define and compare ratios of vector lengths at a point and angles, but not the lengths themselves. And we can also use it to construct something called conformal Christoffel symbols, which is just like the regular Christoffel symbols, but they're made out of conformal metric. You can define conformal covariant derivative, and you can also define conformal connection curvature tensor, which is distinct from the wild tensor. Now, what's the utility of this? Well, usually when you're constructing conformal invariant theory, you pick a member of the equivalence class of conformally related metrics. You do whatever you need to do, and then you show how the result is invariant under the conformal transformation. Well, if you work in UCPR, you can untangle the conformal part from the 4-volume structure. Okay, so you don't have to mix them. And also, you have a sort of a physical meaning. These two structures have a physical meaning, and they're separating. You actually see what they're doing. Now, what I've showed you so far is not new. People have been doing this for a long time. Metric has been split up and divided. What is new in UCPR is what happens with the connection. So, in general relativity, you can write a connection in terms of something called projective parameters or coefficients, and a trace of the connection. So, these projective parameters, they are they're not a connection. They're not a tensor. They have these really strange transformation properties, but they're important, and specifically they were important in Ehlers-Pirani and Schild axiomatic construction of sort of Riemannian space-time, because they define the paths of freely falling massive particles. And what I mean by a path, I mean curve minus parameterization. So just a trace in space-time. So they don't tell me anything about the affine parameter along the path. They just tell me about, so they tell me about the equivalence class of curves which differ in parameterization. But projective coefficients, they're this odd. I didn't want to put them on because there was no purpose, there was no pedagogical value for it. They look messy. Now, what happens in UR? So even Einstein, when he was trying to figure out what he can do with this new way of thinking about stuff, noticed that even though the covariant derivatives, as you define them, don't change, so he says the extensions of tensors by covariant differentiation cannot be replaced by simpler cases. He notices that if you look at the divergence of a vector, the things get simpler. So the divergence of a vector will contain a term which includes a trace of the connection. And that's kind of tucked in because his connection is Christoffel symbols. You get this extra term which depends on the square root, depends on the determinant of the metric. But he says if I have this unimodular, he doesn't use the word unimodular, but in this new formalism, I can simplify that. So my divergence is just a regular one. It's not, I don't need a covariant. Now in unimodular conformal projective relativity, that comes out really nicely because if you adopt the unimodular invariance, T.Y. Thomas in 1925 showed that what happens to the projective parameters is that they turn into a connection. And so you can start off, you can begin with this projective connection and this affine one form as independent fields and then define an affine connection from the two. But you take the projective connection and the affine one form to be fundamental. So this projective connection is a traceless symmetric connection, at least in the cases that I looked at. Again, it has odd, not odd, but complicated transformation properties in the general linear group, but it's nicely in connection. There's a reference to the T.Y. Thomas paper. I've come to really like T.Y. Thomas. I can't find a picture of him. Yes?
Can you understand this one form as in some sense in the engaged field of the global scale transformations?
Yes. You'll see later on. I haven't had time to really dig deeper in this, but yes, it's a possibility, yeah.
So there's a structure that Dirac studied, is that?
Let me just go and then we'll figure out. Okay. Anyways, I was saying T.Y. Thomas, he's done so much that I've used, and I still can't find a photograph of him. So if any of you know what T.Y. Thomas looked like, so I can put his picture on a slide, let me know. He wrote his really short papers, maybe like 2 pages, but were very deep and very helpful for me. So projective structure, as I said, it determines the path. So unparameterized curves of the freely falling massive particles. So if you write down what that might look like, you end up with a 0 at the end, but the path is defined up to this affine parameter. So we can construct the projective covariant derivative, which I know with nabla bar. And interestingly enough, if you take the divergence of a vector with the projective connection, because projective connection is traceless, the divergence ends up being just the regular derivative, which is what Einstein sort of intuitively figured would happen. You can also define projective connection curvature tensor, which is different from the usual projective part. Well, it is different from the projectively invariant part of the affine curvature tensor. So P here is what you get. This is so the P is what's traditionally in literature, it's everywhere, is the projective invariant part of the curvature tensor, but it's distinct from this thing here. And then you have the affine one form that essentially determines the affine parameter along the path, right? So what you end up with is a framework, really. It's not a theory, it's just a framework that allows you to construct a relativistic theory in terms of these 4 fields which have clear physical interpretations. If you assume that they are a priori independent, you can impose compatibility conditions between any pair of them, or more than 2 or 3 of them, without restricting the other ones. So for example, if you want to know if null geodesic paths are autoparallel paths with respect to projective connection, okay, so if I have if I take a null vector at one point and parallel transport it with respect to the full affine connection to another point, will it be a null vector at the other end? And this is also known as a while condition. You can impose that condition separately without imposing any condition on the determinant of the metric. So that's still free roaming. You can impose the EQUI-AFFINE condition, which basically is satisfied if your 4 volume element is path independent, right? So this relates the volume form with the affine connection. This is also related to the second clock effect. So in a wild space, 2 clocks which are traveling along different paths from point P to point Q will have different ticking rates when they arrive there, which they shouldn't. So this condition fixes that. Gets rid of that. Now this full conformal projective compatibility, I really am not sure what that means exactly yet, or if it's something that's physically meaningful, but I can write it down and think about it. So if you have any ideas, you let me know. By the way, I'm desperately looking for people to work with me, so any thoughts you have would be helpful. And then you can get your full-blown, full metric-affine compatibility. It just comes out of it. So the volume form and the conformal metric determine the metric. The projective connection and the affine one form determine the affine connection. But you can impose the EQUI-AFFINE conditions on the little ones on the top without affecting the projective or conformal structure. You can impose a while condition, which actually involves 3 out of 4 structures. And in those 2 are satisfied, then you get your full metric-affine compatibility. But you don't have to force it to begin with. Okay? Another thing that's nice about this is you have 4 fundamental fields, so you can choose which ones are dynamical and which ones are not. So if you have a fully background independent theory, none of these are fixed. They all could be dynamical. And for example, in general relativity, I can start up with the same action as the usual Einstein-Hilbert action, but if I just simply replace or substitute instead of the metric, the determinant of the metric and the affine connection, the projective connection, the affine one from and I go through the song and dance of variational principle, what I'm going to get is first thing what you would expect. If I vary with respect to it should be a tilde there. With respect to the conformal metric, I get the traceless Einstein's, the traceless field equations, and the varying with respect to this volume, for volume measure field, I get the trace. And then the other 2 I still am working on. You get these long, not very pretty expressions, but they're equivalent to full metric-affine compatibility. I haven't figured out exactly how to relate them, but they're equivalent to either to a combination of the EQUI-AFFINE condition and the while condition. You get partially background independent theories. You can decide to fix some but not the others. You're free to do whatever you'd like. And then if you want to fix all of them, then you have a background dependent theory. Did I go too quickly for you? 30, 40, 35 minutes? A long time. Okay. So I'll just summarize. The key point I guess I wanted to get across, and maybe I should reiterate it, is that adopting the unimodular group does not change the physical content of the theory. Basically, when you're dealing with general relativity, you have these densities, and so whatever, your field equations, all the laws of physics are tensorial. So whatever densities you have, they have to be paired up with other densities to get rid of this factor, transformation factor, if you switch to another coordinate system. What adopting unimodular theory does is just basically gets rid of that baggage. You just sort of reassign the transformation properties in a way that you get the same thing, but it's cleaner. The other thing that's nice, it allows for more direct construction of conformal and projective invariant theories in terms of the conformal and projective structures, which are now a tensor and a connection. And again, it provides the flexibility to construct any number of theories. It's a framework, it's not a theory. I think this is particularly interesting in terms of quantum gravity, because now you can quantize some, but maybe not all the structures, and you can think about what should or should not be quantized. I don't know, does the causal structure need to be quantized? Do you quantize the volume form? But that's Lee's job. And in the end, you don't have to take it from me. Take it from Einstein, who I'll repeat. Nobody who really grasps it can escape from his charm. Okay. The sad story is that he published an addendum to that paper in which he actually backtracks. And he says, I'm going to go to the case where the determinant is -1, and I'm going to still argue that the field equations are going to be invariant under arbitrary transformations. But But I think if you were familiar or well acquainted with conformal and projective structures, you probably would have found this to be an interesting, if nothing else, an interesting way to look at things, because it breaks things down to something that's more, it's more fundamental. I guess it has very clear physical interpretations. And he did get one. Thank you.
We have lots of time for questions. John?
Yes.
Just a historical thing, it picks up on exactly what you were saying right at the end there. So November 4th, he's got the unimodular theory. November 11th, you lament that he backtracks. Well, you can make the lament even stronger because it was a complete disaster, the backtracking. Because if you've looked at these papers recently, but my recollection of them is this. He tries to keep the unimodular condition, which was enabling him to discard certain terms in the Riemann tensor to get the Einstein to get his field equations. In order to avoid dropping those terms, he makes the physical postulate that all matter is electromagnetic or rest mass free, so that he could make the trace of the stress energy tensor vanish, and then he could make one step up, and of course to the November 11th theory. But that was, but when you're reading through the papers, you have this sense of the guy's desperate, right? He'll do anything to get general covariance here, even this crazy physical assumption that is not going to survive, more than a week or two.
The other thing, at that time, he was splitting the Ricci tensor into two parts that he later abandoned. He called them R and S, and the Ricci tensor was G.
Yeah.
So he was taking the first, one derivative and one cross term as a separate entity, and then.
Yeah, that all goes back to the Zurich notebook. It's already all there. The stuff in some of the stuff in the gosh, it's been a long time since I looked at this, so I might have it wrong. Some of the stuff in that November 4 paper, he already had earlier on. The difficulty for him in the Zurich notebook was to get the Newtonian limit out. We now know how to do it just by using coordinate conditions. So he hits upon the harmonic coordinate condition, which is the one we'd normally use, and it does a great job. He convinced himself that wasn't good for various reasons I won't go into. So he started looking for other ways of getting the Newtonian limit out, and this was the way that he'd do it. He'd take the Ricci tensor, break it up into two parts, and then he had a weakened coordinate condition that could then reduce just one part down, and that I think is still there in the November 4th paper. If you look towards the end,
I think so.
Yeah, and he's got this funny coordinate condition that no one would now normally use. That has been transported just in its entirety from the Zurich notebook. So it's interesting because there's correspondence elsewhere where he says that he'd already hit upon these equations and I think turned away from them with a heavy heart or some expression.
Do you know if there are any notebooks that covered this? I mean, do you have any idea if there are notebooks that will contain calculations from this part? Because it's in that time period. I mean, he just.
Yeah, the stuff that I know pertains to the discovery that the N4 theory was defective, and he realizes he thought he had covariance under the rotation transformation, and when he realizes he didn't have that was then he just collapsed in despair. And there's correspondence around that where there's a very sad letter he writes to Freundlich, the astronomer, and also his friend there, saying, I think it's got this line, my brain matter is so, do you remember, is so stuck in a rut that I can't see my way out. I need someone, with fresh thinking. Of course, Freundlich was exactly the wrong one to go to. He didn't do this stuff. But it's I don't know. There's a bit of a blackout around this time because Einstein's rapidly calculating and sending through communications, and so he suspends correspondence with almost everyone except Hilbert. So, sorry, I wish I had more for you. But certainly, the November 11th step was a bad move. Yeah, boy.
That broke my heart.
Yeah.
Michael.
I just have a kind of question of information. could you help me understand the physical significance of the 4 volume? I understand the the physical significance of the conformal structure and the projective structure?
It's a measure, so it tells you how much volume there is.
Right, but
in
what's
that
the physical
parallel
significance of it?
I don't know. I guess it would be whatever you would measure with rulers and clocks. It's a 4 volume.
Okay.
It's how much space and time there is there.
Carla was next.
Yeah, so in the metric-affine theory,
Mm-hmm.
if you take the Einstein-Hilbert action and just vary the metric and the connection
It's
separately,
Palatini,
you
right, yeah.
automatically get metric-affine compatibility.
That's right. That's right.
Do you get anything surprising like this as well?
Sorry, what sense?
So if you write down the Einstein-Hilbert action and
Mhm.
start varying your independent
Right.
variables independently, do they couple automatically?
Yeah. So that was the. So this was. I'm gonna go back. Sorry about this. So I did do that, and so you get something that's equivalent, but when it comes to the compatibility, it doesn't come out as clean as I'd like it to. So it will be in this part. So when you're varying with respect to the projective connection and the affine one form, which is also called projective one form in literature, I just recently discovered. So it doesn't look as pretty, but it's equivalent to these two. So I'm actually trying to figure out if there's a different Lagrangian that could give me these conditions, the equi-affine condition and the Weil condition from the variation. But I haven't gotten very far.
And is there any kind of understanding how the most simple action would look in these variables? Is it the Einstein-Hilbert action, or is there like a class?
You know, I think the Einstein-Hilbert action, if you write it in terms of these 4 structures, I looked at it and it looked to me like the simplest combinations that you can possibly get, right? I mean, if I take 4 fields and say, okay, well, how can I put them together? This is what it looks like. But I don't know. I haven't gotten anything yet. I've been trying to figure out what would be a good one to start with.
And one last question, if you found a more general action,
Mm-hmm.
would you expect to be able to explain some physical phenomena that were actually measured? Or do you think the content of the field is just so much the same as in GR that you won't, like dark matter or dark energy?
So this is a formalism, right? You can do anything with it. So you could start with a Lagrangian that might explain dark matter or dark energy. You know, I haven't convinced anybody yet successfully to pay me to do this. So my life belongs to my students who have very different ideas as to how I should be spending my time. This is a vacation for me. But I think that's definitely a possibility. I talk to some people who do FOR theories, trying to account for the inconsistencies between GR and the observations. But it's a lot of, you know, imagine how they have RR squared and so on. So it's a tedious and long process. I haven't gotten to any, I've done some work, but I haven't gotten any nice results yet. But that would be the hope, right? That would be the goal. So starting with these sort of more basic structures, can you construct a theory that makes up for whatever the GR doesn't do in the light of the observations in cosmology and astrophysics?
I think Lee was next then, though, right?
Yeah, at least, it doesn't matter. There's a different chapter of the story I know, so it's fascinating to hear this chapter, which is, I'm pleased about the relation of it. The chapter of the story I know was a
Sorry.
Speak
Can
up
you
a
speak a
little
little
bit.
louder?
There's a chapter
Everyone
of the
has to
story
speak
of
up.
unimodular gravity that I'm familiar with, which starts with a different paper of Einstein in 1918,
Mm-hmm.
in which he observes that the cosmological constant is the constant of integration. And that's,
But the assumption there is that you start off with a metric which has a unit determinant, right? And then that
Yes.
constant, that degree of freedom shows up as a constant integration.
right, so there are then 9 field equations and not 10.
Mm-hmm.
And you get the trace-free Einstein equations, RAB minus 1/4 GABR. And then you take the trace of that and you have a constant integration, which is the
Mhm.
cosmological constant. And there's been various speculation about whether this might resolve, quote, the problem of the cosmological constant of dark energy.
That was your paper, right? You wrote a paper in the module.
I wrote a paper on a small technical side issue. Can
I
do
remember
it
you
that
sending
way?
it to me to read it, and that was before I did any of this stuff, and I was just like, so I never wrote back, and I felt bad about it.
Yeah, I was concerned with whether in a quantum theory the measure could be compatible with this assumption.
Well, I mean, I looked into that. I haven't pursued it in more thoroughly because of what I was saying. I think it's a more restrictive condition on the metric than I like it to be, but it's possible that this volume 4 form actually, ends up, depending on what you start with, explaining the cosmological concept. I just haven't had a chance.
But maybe a question for you or for the historians. So this idea appeared twice in Einstein's work, in 1915, which I was unaware of before your talk, and then in 1918 in the paper in which he shows that the cosmological constant is a constant of integration, because he's already embarrassed by the cosmological constant and trying to put it in a loop of life. Has he dropped the idea in between?
Yeah, I think he did. Well, I mean, he dropped the idea of the metric with the unit determinant, right? He went back to the full diffeomorphism group and whatever, general covariance, and then that kind of fell out. But he kept, most of his review papers, he says, I'm going to write the equations in a coordinate system in which the metric has a unit determinant. He always says, even though we do that, the equation is still going to be, generally covariant, because this is just a special coordinate system. But I don't think...
It's different to go to a special coordinate system for the full
Right.
figure.
No, I understand it. So what I'm saying, I think he dropped this unimodular stuff and then went back to the...
I see. Okay, very interesting.
Could you go back to the slide that had the advantages and disadvantages of
Yes, the summary.
and particularly the one on the G minus 1 value for G.
Oh, I see, with the... But which one was it? One towards the
It
end?
was very, very close to the end.
Oh, this one, the summary?
Yeah. Now, what would be, can you say something about the disadvantage that comes from eliminating densities?
I cannot think of a disadvantage of eliminating densities, but the price you pay is that you have 4 fields now. So you have to do 4 times as much work.
Okay.
Yeah.
Because it would be that would be something that might be worth exploring.
I mean, densities are a nuisance. You get all these extra terms.
Okay.
Yeah.
Yes. First Ryan. Sorry, I don't know your name. The guy behind Ryan.
Things?
C.
Things?
So who's first? Okay,
Oh.
Ryan.
Right, thank you. You mentioned very briefly the EQUI-AFFINE reconstruction. That's something that I know is really rich, fruitful to think about. And you mentioned joint work that I think tied into this project about this is another way of reconstructing the theory. Would you mind saying a few words about that?
About
Is there any-
EPS?
Well, no, about the continuation of that style of project and I believe you mentioned some work that you've done on that.
Well, what I presented for the last third of the talk is this framework.
So
which
that
is what-
simply is the...
Yeah, it gives you mathematical formalism, which you can use to sort of describe what Ehlers, Bradonjic did. So they said, okay, so you have a projective structure which represents an equivalence class of curves traversed by massive particles. You have a conformal structure, and then they oppose different compatibility conditions between the two.
Sorry, I'm just being slow. The compatibility conditions that you mentioned
Are in there.
that are in fact
Right, that's right.
the
So
corresponding compatibility, the conditions that correspond formalism to
that's right.
those proposed.
That's right. So the bottom one, the wild condition, I think the first condition that they have is that, and they have sort of a graphical description of it, is that you have a null cone at a point and then all the autoparallel paths of the projective structure fit into null cone. So the null cone, the null rays that pass through that point are also the autoparallel paths of the projective connection. And then the second condition, which is the EQUI-AFFINE condition, I'm pretty sure is equivalent to this. The problem with the first condition is that we end up with a while space, where you have this path-dependent ticking rate of the clock. So to fix that, they impose another condition that the clocks tick at the same rate when they meet. And so that's embedded in the EQUI-AFFINE condition.
If I could just make a comment on that, or ask for more clarification. So the question you're asking was more like, does this suggest another kind of, or a continuation of that kind of constructive axiomatic approach? Or is what you're saying is more that it's a framework within which, because of the way the fields are distinguished, it's a possible framework in which to develop such an approach, but it doesn't really determine one
Right.
in particular.
Right. It's just, you know, you have these fields with clear physical interpretation, so you can maybe start thinking about it in a more formal way, because the issues with Euler's Clarence, there were many, I understand, and people looked over their work and tried to be more rigorous with what they did because they weren't very rigorous to begin with, and I think this formalism makes it easier to be more rigorous with it.
Okay. So, Steve?
I had a question about the constant volume that you were speaking about. So let's say that, I'm not sure about this, maybe I've been wrong. Let's say I go from one point to another point. The vector changes its direction. So basically, can I come up with going from one point to the other point when the two vectors that have an angle with each other that form a volume, the three vectors that form a volume, two of them coincide with each other or come up to make a surface instead of a volume?
I see what you're saying. I think that's restricted by having a non-zero determinant. Because these are ordered basis vectors, so there is an orientation to them. And so the transformations are not supposed to change the orientation. And so the only way you can change it, Lee, can you watch what I'm saying here and let me know and tell me if what I'm saying makes sense? So his question is, actually all physicists, if I have a basis in one point and I move to another point, can it happen that the vectors get transformed in such a way that I don't have a full volume anymore, that my vectors collapse, right? And I don't think so, and I think that restriction
It
is,
wouldn't be invertible. If the volume element went to zero somewhere,
yeah, you can't go, right,
that parallel transport wouldn't be invertible.
right. Yeah, so that's the restriction, that delta cannot be zero, right? And in this case, it's always one, so there was no, so what I was saying was right.
And also, like, in your equations, in your slides, we had a factor of 1/5.
Yep, that comes from the projective invariance. So if you write, if you want to write the condition, sigma mu nu, so you get, that just works out so that when you take the trace of the affine connection, what you get is that one form. So you have P sigma mu nu plus 1/5 sigma mu gamma nu plus sigma nu gamma mu. So if I trace over sigma and mu, this will be traceless, so that will go to 0. And then this term, this has to be mu. This term will be 4, and this term will be 1. So I get factor of 5 up front. So that just ensures that that is the trace part of the affine connection. Is that what you were asking
Yes.
about? Yeah.
And I have one last question. Like, I think I may be wrong again, but in your last slides, you mentioned that we can fix some frames and work with others. You had 4 cars, you put pin on 2 of
Oh.
them.
Okay, yeah, I know what you mean. So keep some fields dynamical and keep other constant?
Yes.
Is that what you mean?
Yes. So what makes us do that, like working, and especially you said in the summary that we can use this in quantum gravity, making some fields constant and working with others. What is the basics of doing such a thing?
Well, it depends what kind of world you're describing. So if you're dealing with a special relativistic theory, right, the metric is going to be fixed. So you're going to have a Minkowski metric everywhere. So if I want to use this formalism to construct a special relativistic theory, I would fix those two fields, right? I mean, it just as an example, right? So it depends what you want to do with it.
So am I fixing the experiment with the mathematics, or I'm just writing the mathematics and doing it in different styles?
You're doing whatever you want with it, essentially, because it's a formalism, it's not a theory, right? So if you take general relativity to be the theory that describes the universe, whatever, and all the structures are dynamical and it's a background independent theory, then you don't make any of them fixed, right? They're all dynamical. But if you need to construct a theory which is, has some things fixed, you fix them. And in terms of quantization, it's, you can have a classical field that's dynamical but not quantized, right? So that's a separate issue. I gave you a lot of time for questions.
Is there a question?
No.
Okay. Any other questions? I have one.
Yeah.
You mentioned in your talk, you posed a difficulty about proving compatibility, I think, of the conformal and
And projective?
projective, but then it seemed like in the comments afterwards, you basically gave an intuitive account of what that means. So is it just a failure of having a rigorous?
The wild
proof of-
condition also involves this trace of the connection. So the one, do you referring to the one that I mentioned about Euler-Speronian Schild? The
Right.
null clone? Yeah, that will end up actually, it leads to a wild space, so it will involve this third field, whereas the conformal projective compatibility, which I'm still trying to understand, does not. It only imposes a condition on the projective structure and the conformal structure.
Okay, and there isn't a rigorous connection between just those two that doesn't involve.
Yeah, I don't know why. It's not that there isn't one. I just don't. I'm trying to figure out what the interpretation is. What is it?
There's a kind of history of becoming more rigorous, right? Because all this began with just a kind of suggestion by Weil
Right.
that was only thinly disguised as an argument, right?
Mhm.
That such a construction of the metric from projective and conformal structures was possible.
Right.
And Euler's Brownian Schild was supposed to be a kind of rigorous account of that.
Right. But even Euler's, it's not a question of rigor. It's a question of like a physical interpretation. What does this mean? So the first condition in Euler's Brownian Schild is the wild condition. It's the one that involves three structures, not two, because it is the part that says, okay, if I have a covariant, this is a full affine connection, it's going to be proportional to the metric. This contains in it the trace, right? So it involves the projective connection, the trace of the affine connection, and then actually what happens is that it restricts the metric only up to a constant. So you essentially just have a conformal metric. But the projective conformal only deals with this is the projective area. So it does not have, I'll use operator. It does not have the trace of the connection, or the affine connection there, or the formal. Do you understand? Am I answering the right question, or is that?
Yeah, I wanted to know what was the origin of the difficulty.
For them or for
For you.
for me? Well, it's just not knowing what it means. I still don't know what it means. It might be completely meaningless. I don't know. But I think it's my responsibility to write it down and think about it.
Lee.
Yeah, I'm reminded by the last equation here, which is when you just have a conformal metric and the phi field. Dirac, I don't remember the year, but I think it was relatively famous, like Dirac considered the theory with one form field and with this relaxation measure compatibility.
Okay, I'll look into it. Do you remember? I'll get the reference as much of it as you can remember from.
Yeah, I have it in a paper which would have to be dug out. But I remember reading Dirac's paper, and there wasn't any sign of the previous, that he was aware of any of the previous history.
Further questions?
I think everybody wants to get lunch.
Well, thank you very much.
Thank you.